with the Kirk-Tisink model and the dual unitary circuits has been pointed out also by Balakrishnan and Lamakraft, the same, but a few months after our paper on dual unitary circuits. Next, please. Okay, so now this is again, I mean, I'm probably going to go very quick through that because that's just repeating introductory parts of the talk of Peter Claes. I mean, this is like the correlation function we want to calculate. So in the original formulation, so that using forward and backward evolution on a local operator, let's call it a beta. And so I can still use my pointer, right? You still see my pointer, right? Or not? No, you don't. No, you don't see because it's shared. You don't share. Okay, sorry, that's a bit of inconvenience. Sorry. So basically, that's the way how you present the local correlation function, and okay, and I mean, what you can do immediately. I mean, for example, you can take arbitrary pair of local operators. I call them A beta and A alpha, where alpha and beta are two kind of Pauli indices or generalized Pauli indices, which go from 0 to d square minus 1, where 0 means identity operator and 1 to d square minus 1 runs over all Hilbert-Schmidt orthonormal traceless operators like Pauli matrices, Gamma matrices, and so on. And then you can write this correlator exactly in terms of, I mean, this is like translation invariant circuit, translation invariant in space and time. Then you can easily reformulate it in terms of some correlation functions which are homogeneous in space. So they are only functions of the displacement between two operators. But of course, there is a staggering structure, so we have to define two correlation functions like C plus and C minus. Next, please. And right, and then using unitarity, then you can immediately find that I mean, using unitarity and dual unitarity, you can show that correlation functions can only spread along light rays, and there they can be written in terms of completely positive maps. Next, please. These completely positive maps, which also Peter has introduced, so n plus and n minus, which are basically unitary channels, which are written in this standard representation in terms of the d square by d square unitary and partial traces. Next, please. And then diagonalizing these maps, n plus and n minus, one can basically find explicit expressions for time correlation functions of any local operators along the right rays, right? These are written now in terms of spectral decomposition of n plus and minus. So the eigenvalues are written as lambda plus lambda minus sub gamma, where gamma runs over eigenvalues. Gamma equal to 0 corresponds to trivial eigenvalue, which is always equal to 1, which corresponds to unit eigenoperator. That's always there because of the structure of the problem. But the other eigenvalues actually can basically teach us about ergodic and mixing behavior of the circuits. For example, you can have a full ergodic hierarchy. For example, if all eigenvalues, all non-trivial eigenvalues, can you go next, please? If all non-trivial eigenvalues are 1, this corresponds to a swap gate. If some eigenvalues are, next, please. If some eigenvalues are 1, but not all, then you can have ergodic, non-ergodic, but still non-integrable behavior. If some eigenvalue is, if all eigenvalues are different from 1, but some are in unit circles still, then you can have ergodic and non-mixing behavior, like indefinite oscillations. And then when all non-trivial eigenvalues are within unit disk, then have ergodic and mixing behavior. That's the generic behavior for almost any gate. Next, please. Now, what is an interesting problem is, of course, to classify all dual unitary gates for a given dimension D. And as you have seen, it should have probably been clear from Carol's talk, this is a difficult problem. It can be completely solved for d equal 2. Then writing this so-called Cartan decomposition of U4, you can immediately find, and that was very nicely explained this morning, you can immediately find a complete family of dual unitary gates by setting these two Heisenberg parameters equal to pi over 4 and the third one to be arbitrary. Next, please. And now this corresponds to kind of interesting special cases like swap, where the other parameter is pi over 4, or integrable gate, when, where all these decorated single unitaries are identity. Or one can actually even write the self-dual Kick-Teasing propagator precisely in the form of a circuit in terms of this notation. Next, please. Yeah, and then, as you have heard in the previous talk, there is a nice generalization of this parameterization, as it was elaborated by Peter and Austin. And then there is also other generalizations, like the one which has been described by Boris Gutkin and his group, which generalizes Kick-Teasing model to higher D. Next, please. And just to tell you basically that this is not all, and that even the parameterization that has been elaborated in the previous talk is definitely not covering a substantial part of the manifold of dual unitary gates. For example, the one which Peter was introducing had the total number of parameters, which was scaling by this as d square. In his notation, I think q square. So local Hilbert space dimension square. But one can immediately show that there exists a submanifold, perhaps not very non-trivial submanifold, so quite saturated submanifold of dual unitaries of dimension d, which has dimensionality d cube. So the unitary group of d square has dimension d to the 4. The simple, well-known parameterizations have dimension d square. But what you can easily write is also parameterization which has dimension d to the cube. And that is again written very easily in terms of this canonical decomposition of dual unitary in terms of a swap times a V, where V is a partial transpose unitary. And a partial transpose unitary can be written in terms of this Schmidt decomposition, which is not exactly canonical Schmidt decomposition, because this B alpha need not be orthogonal. But what we need is that B alpha is unitary. For any B alpha unitary, this will be actually the U should be unitary, and the reshuffled U should be unitary as well. So U should be dual unitary. So in the simple parameter counting tells you that B alpha, each B alpha is parameterized by D square parameters. There are D of those, so there is in total D cube parameters. So for example, this is to me at the moment the largest family of dual unitaries in D dimensions. Next, please. And of course, there is a couple of, I'm sorry for that incomplete list, but there is a couple of recent paper. There is a lot of activity in various groups recently on using this space-time duality even beyond the concept of dual unitarity in various directions. Many of those will be discussed in this workshop. Next, please. But I will actually now focus on discussing some simple problem of perturbative or structural stability of dual unitary circuits. So let me now try to spend 1 or 2 slides in order to generalize or compactify this discussion of correlation functions. So this I will do by using this so-called folded representation, namely by just folding the correlation function circuit back to itself. You can write it as a simpler circuit. For example, by introducing this green gate, which will be like now I'm using these wedges to indicate orientation of the gate. So if you flip the gate, then the wedge moves down because the gate is flipped top down. So you introduce the green gate, which has thick wires, as the folded blue and red gates, and one of them is transpose, conjugate, and the other is transpose because it's flipped top down. Moreover, what I do also is I use thick wires, which means I now use wires of dimension d square, which now corresponds to vectorized states, namely, for example, for qubits, these are 3 Pauli matrices plus identity. Sorry, what's that now? Sorry. Okay, right. So again, I'm using the same correlation function as I noted before. So now I'm using 2 local operators A and B, placed by t half steps apart. and displaced by y in the spatial direction. So in principle, now these operators need not be on the light ray. They can be inside the light cone. So if they're inside the light cone, then the correlation function circuit is basically a rectangle, right, of dimension, which is x plus t and t minus x and t plus x. So the longer dimension is t plus x, and the shorter dimension is t minus x. So for convenience, we decide now to flip this, to turn this rectangle for 45 degrees. So we really have a rectangular kind of partition sum representation of correlation function. So now a general correlation function, and that's the simplest object in many body physics that you want to calculate, which is already intractable in general. So the problem of dynamical correlation functions in this business now is replaced with the problem of finding partition sums of some statistical-like models with non-trivial boundary conditions. So there are these A's and B's which give non-trivial boundaries, which are like point defects at the boundary, and all the other points at the boundary are kind of trivial, are basically corresponding to the circuits, and circuits means like taking trace or joining the wires, which corresponds to Bra and the cat. So it's either taking the trace or taking the unit operator, depending on which direction you're looking at, dual or forward, or flipped or forward. Okay. Okay, next, please. Right. So now what I'm going to discuss now is basically how to, of course, this is an intractable problem, so we cannot do anything. And right, even Monte Carlo, of course, as you know, doesn't work because there is sign problems everywhere, so you can't really organize whatever computation you have designed. So we need some other ideas. So an idea is now to use dual unitary circuits, which are almost non-dual unitary circuits, which are almost dual unitary. So the idea is let's take a dual unitary gate. Let's take a gate which is dual unitary times a perturbation, and perturbation will be written of the form which is near identity. That is e to the I eta p, where p is Hermitian and eta is a small parameter. So let's say any small perturbation of dual unitary gate can be written in this form for appropriate Hermitian perturbation p. Now, what we decide is, of course, what you can decide now is to perturb all gates or to perturb just a small subset of gates. We can study both cases, and in the paper that I mentioned here in this PRX, we actually study both cases. We study either low density of dilute, let's say, perturbations, where we just take perturbations with some density delta, which we denote in the paper. So low density, small delta, or density 1 and small eta. These are the two cases. But I mean, from the point of view of, let's say, rigorous analysis, it's much easier to discuss low density regime first. At least this is the one which we can control. And the high density regime is basically relying on some numerical observations, which tell us that it works equally well. But we still don't understand all the reasons why it works well. So let me just focus in this, for the purpose of this talk, to the low density of perturbations. And okay, so now let's just imagine this picture below. This is the kind of correlation function we want to evaluate. The yellow gates are dual unitary, and the green gates are arbitrary gates, which are perturbed dual unitaries. So for dual unitary gates, you have unitarity and dual unitarity. So the unitarity and dual unitarity are written on top row of my slide. So the green gates satisfy unitarity, which means that when you just press circles from bottom and from top, you get straight lines, right? But yellow gates on top of that also satisfy sideways unitarity, or better call it unitality now, right? It's actually corresponding to unitality of a supergate, let's say, generator of a master equation. So now we have the sideways unitarity or unitality on top of that, right? Which is written in terms of these sideways contractions. Right? This is exactly equal. This is exactly generalizing this, or it's equivalent for unitary gates to this other diagrammatic notation of dual unitarity, which was written a few slides back, or in the talk of Peter Claes. Okay, so now the idea is, the idea which we want to kind of justify or derive here is the following. Let's kind of imagine that this intractable correlation function, which is the left-hand side of the expression below in my slide below, can be somehow decomposed into a sum of paths, where each path is a contraction of a one-dimensional transform matrix. So path means basically you start from A and you end at B, and you just go along a one-dimensional path, where this animal which connects A and B is contracted with circles sideways all the way. So this is really just applying finite dimensional matrices and multiply them along the way. And then there is a sum, right? And this sum means basically summing over all possible paths, where you can only go straight through the yellow gates, because yellow gates don't allow you to turn, because, as you know, you can only the straight lines corresponds to light rays, right? And this is now 45-degree tilted representation. So straight lines, horizontal and vertical, corresponds to light rays moving diagonal to the west and diagonal the east and diagonal to the west. So, but of course the green gates are arbitrary. So the green gates allow for turning, right? So there is this idea that maybe there is kind of a path integral representation where you can just expand a non-tractable correlation function into a sums over paths, and each path can be efficiently calculated by powering a matrix, finite matrix. So it's like a Feynman path integral idea, right? You have a many-body problem, you reduce it to a path integral, which is like a single particle problem, right? But then again, there is a sum over paths. So next, please. Okay, so now first, before, in order to be able to proceed, by the way, how much time do I have?
About 10 minutes more.
Okay, thank you. So in order to proceed, we make additional simplification, and that simplification was also mentioned in the last talk. Namely, we replaced our quantum circuits by classical stochastic circuits, which are actually derived exactly from quantum circuits in presence of U1 random noise. So you can imagine that you decorate your gates with random fields, but these random fields all act in the z direction. So it's like you have a parameter h with subscript j and t. J corresponds to position and t to time, and you take h, j, t random Poisson variables, so random IID variables which are flat distribution between 0 and 2 pi. Now, if you do averaging with respect to those, you can average the correlation function. Correlation function is a two-point object. So if you average correlation function, for example, if you would take even more random fields, if you take just completely like random fields in arbitrary direction in space, then this would correspond to like H-random average correlation functions, right? Or H-random average circuits, and then this would trivialize correlation function. I mean, any correlation function would be just a delta in space and time. But if you do this averaging only with respect to U1 noise, not SU2 noise, then actually what you're left with is still a non-trivial dynamics, but which is essentially classical stochastic dynamics. So basically now you can rewrite everything in terms of a basis of diagonal operators. I mean, these dynamics, this random U1 average, U1 noise random average dynamics basically reduces the Hilbert space of operators to two states, to two operator states, namely to two diagonal operators. It diagonalizes the dynamics. So you only have to worry about identity and sigma z. So the non-trivial dynamics is only mixing identity and sigma z. So basically you can write now your gate, which before was a 4x4 gate. Before was a 16x16 gate, because the local Hilbert space, the local operator Hilbert space of folded Hilbert space was 4-dimensional. Now this folded space reduces to 2 dimensions, just spanned by unity and sigma z, which I will later denote simply by a bullet, which is a non-trivial operator. And this 4x4 matrix now can be parameterized completely. And the fact that it is bistochastic, namely it needs to be bistochastic because that's a consequence of unitarity. So bistochasticity of this matrix, I mean, this is just like a stochastic matrix, but in a Hadamard, I mean, after Hadamard transformation, if you want, right? I mean, in the standard bistochastic matrix would have sum of rows and columns equal to 1 in each row and each column. But after this Hadamard transformation, this corresponds to a matrix which has in first row and first column only zeros, unless row and column equal 0, right? And all the other elements are arbitrary. But now if you want this matrix to be to correspond to dual unitary matrix, that is after this stochastic projection, it corresponds to something which I would refer to as dual bistochastic. I mean, again, you can make a space-time flip, or again, you can make a reshuffling if you want. Now, reshuffling will not be the same quantum information theoretic thing that Carl was discussing, but still you can make this reshuffling of indices, and that this would correspond. I mean, you can make space-time flip, and then bistochasticity will now correspond to dual bistochasticity, which would, in addition, fix these two parameters, which are denoted by p epsilon and q epsilon to 0. So epsilon, putting epsilon to 0 would correspond to a dual unitary matrix, to a projected, stochastically projected dual unitary matrix. Next, please. Okay, and now it's a kind of, you have a very nice kind of diagrammatic representation of arbitrary correlation function. Of course, now you can study, if you want, stochastic Markov circuits, like a brickwork Markov circuits. With this dual bistochastic property, you can still see that you can exactly compute correlation functions, and these correlation functions are non-trivial on light rays, the same as before. So from, let's say, mathematical physics perspective, physics is the same as for dual unitary circuits, but it's much simpler because the local Hilbert space dimension has went from 4 to 2. Okay, now, so now we have this nice interpretation of the correlation functions in terms of tilings of a plane. So again, imagine now you have this t plus x times t minus x rectangle, and you have the initial operator and the final operator, which are these sticking out tiles with sticking out wires. And now you have to basically write a correlation function in terms of tilings, which are admissible in the sense that there is no, I mean, that's just a simple way of, accounting for forbidden processes, namely that you shouldn't get any zeros in this multiplication of matrices along the way. So, so what it means that it's this, this amplitudes you assign to tiles, and and the condition is that there should be no tiles with dangling ends in the tiling, right? So basically, what you have now is this kind of things, and then these things can have these simple paths, or they can have loops, right? And now what we want to argue is, we want to argue then that under some conditions, this correlation function should be expressed in the leading order only as sums over paths with no loops. And we want to have precise condition for that. We want to have precise condition for when I can replace this correlation function in terms of paths without loops. Now, of course, you can immediately see when this is possible. It's possible whenever these amplitudes for branching are 0. For example, there are these amplitudes for branching, like E and F. When you put E and F equal to 0, then you get already exactly solvable situation in which there are no loops, in which this path integral formula would be exact. So there is this either branchings E and F, or other branchings A and D, right? So either you put B and D, either you put B and D to 0, or you put E and F to 0. This will correspond to exactly solvable situations. Another exactly solvable situation, of course, is dual unitary when there is no terms. So, for example, epsilon is epsilon 1 and epsilon 2, which is p epsilon and q epsilon. When these two guys are 0, this means that there are no terms, right? This means that basically if there are no terms, then the only non-zero tiling, only admissible tiling is when these boundary conditions are on the same line and when you go straight. Next, please. Now, for example, now you can think of how to make a systematic expansion in terms of perturbation series in terms of epsilon, right? To first order, for example, for that particular example, when you have these two in and out operators on different corners, then one has to have at least second order diagram. It has to have at least two terms, right? Two terms means two epsilons. It means second order epsilon square. But there could be a path without loops, or there could be loops, right? So, I mean, it's not clear to second order, well, then there are no loops, right? Next, please. But now we have identified a precise condition for which we can claim that that the paths, that the diagrams with loops don't contribute in the limit of dilute perturbation, and that is precisely these simple conditions that I stated here. So, for example, these A, B, C, D, and F are the parameters of the gate. So when this, sorry, there is a mistake here. This, no, it's okay. I think alpha, beta, yeah, it's fine. So when alpha and beta are singular values of these 2x2 matrices, then when both of these conditions are satisfied, then we can show that the loop diagrams don't contribute in the dilute limit. Next, please. And then we have a simple path integral representation of the correlation function, which we can evaluate explicitly in terms of simple combinatorial sums in case where the perturbations are placed on a regular sublattice. So that formula, which is written in the center of my slide, corresponds to a regular sublattice of correlations, but that's not at all a limitation. I mean, it applies, the thinking or the idea applies to any dilute limit, but in a general, let's say, disordered dilute limit, there would be no explicit combinatorial expression. One would have to just sum it up, but still this summation would be efficient. And the idea is to study these two transfer matrices. I mean, there is this simple, very kind of neat algebraic idea, is that these two transfer matrices, which I wrote in the top of my slide, which are composed of these dual unitary gates, but these are big transfer matrices. They are 2 to the L, actually they are 2 to the L to 2 to the X to 2 to the X. So they are 2 to the X by 2 to the X matrices. And these matrices allow for efficient block diagonalization, recursive block diagonalization, which is accurate, which is asymptotically exact when these two conditions are satisfied, which I wrote above. So I don't have time to go into details, but that is, I mean, I invite you to look at our paper, but there is this particular explicit representation of these transfer matrices which allow simplification. Can you go back 2 slides, please? One more, 2 more, please. One more back, one more back. Still more, this one, yeah. So if you look at this lower left diagram, I mean, you see this, there's these yellow pillars or yellow rows. These yellow rows are in the dilute limit. It means many repetitions of these yellow rows or many repetitions of these yellow pillars. And if you have a nice block diagonalization of these transfer matrices, then you can replace this by simply by leading eigenvectors, by projectors to leading eigenvectors, and then things simplify to this the right-hand side, which are the sums of paths. Can you go back, please, to 3 or 4 slides? Okay, so now then go back. Yeah, that's it. So then what you get now is basically the correlation function. This is just an illustration of how this formula works. And this illustration is already for, I think, parameter values x and t, which are large enough so that brutal calculation is impossible. So in this case, you get a correlation function, which is, again, have dominant contributions along light rays. You see that along light rays, there is this dark, I mean, white means completely 0, but then the code means dark, cold color means smaller and warm color means higher. So you see that correlation function actually goes into the light cone, and actually the dominant, the peak of the correlation function is actually going really to the center, almost to the center of the light cone, but then there is still these contributions along the light rays. And on the right, we show the error, the relative error of this path integral formula compared to the exact computation of the correlation function for several random examples of dual unitary gates, perturbations of dual unitary gates and their perturbations. And for some gates, all gates except for the gate 5 satisfy this condition. That means that that error goes quickly down with epsilon, when epsilon is actually related to eta, it's proportional to eta, this perturbation strength. But the black gate, which doesn't satisfy the condition, basically has error of order 1. Yeah. So you see that it's really like a phase transition between structurally stable dual unitaries and structurally unstable dual unitaries. Yeah. Okay. So with this I would like to close this part, and then we spent the last 5 minutes on something completely different. So next, please. So just a comment. I mean, there is a second paper which I didn't have time to even go into details of, but we use similar ideas in this PRL, which appeared afterwards this year. Next, please. Okay, now something completely different, or not so completely different, but still a different way of representing similar things in terms of what I would like to call dual IRF circuits, interaction around the phase circuits. For example, one can equally represent this nice local many-body interacting dynamics, which we all like to represent in terms of brickwork circuits. You could equally represent those in terms of 3-qubit circuits. I mean, circuits which act on the neighborhood of 3 qubits or 3 qubits. But it acts non-trivially only on the center qubit. So there is a action qubit, and then there are 2 control qubits on the sides. Yeah, and that can be parameterized in terms of the unitary matrices of a single qubit, that is means, sorry, d square unitary matrices, which each of them has d square parameters. So the total number of parameters for each gate is d square times d square, which is d to the 4th, which is exactly the same as the total number of parameters for a general SU d square gate, which is a two qubit gate. So there is the same kind of parameter counting, but it's a different kind of physics paradigm. Yeah. So there is now a notation which I would like to introduce here, which is just a plaquette, right? A plaquette now corresponds to a unitary operator. But I like to use this plaquette notation because it's exactly what people in classical StatMech, like starting from Baxter, were using in order to indicate this interaction around the phase models, right? So now IRF models, of course, are classical StatMech models where weights are positive. Now what I'm saying is that we can just as well replace these positive weights by complex numbers, and we can assure that this complex number corresponds to unitary interactions around the phase. So then we have unitary circuits, right? And actually the special subclass of these unitary circuits are the reversible cellular automata, among which the most prominent is the rule 54, for which many interesting physical properties can be exactly calculated, for example, those which were reviewed in this recent review quoted down there. Next, please. I mean, I'm just giving you in the last 2 minutes some pictorial idea how these things can be kind of expanded in these IRF circuits, and how one can compute, for example, non-trivial correlations using, again, simple one-dimensional transfer matrices. So again, I'm using, to simplify things, just a folded representation. So I can now again fold these IRF circuits back on itself. I can double the wire, so I get a thick wire, and then my general correlation function, which are now local operators, have to be now understood as operators which act on two adjacent sides. So this orange, yellowish orange clouds are now indicating local operators on two sides. And now this will be like a sort of a general correlation function, right, in the folded representation. Next, please. But now, once you assume unitarity, which will be now these are folded gates, the green plaquettes, right? They are folded IRF gates. So now unitarity is the first line of my slide, and dual unitarity is the second line of my slide. If you use all these, then this correlation function, which I showed in the previous slide, is non-trivial only when these A and B are sitting such that they are connected by these simple two-leg ladders. Yeah? So these two-leg ladders are like now powers of correlation matrices, which are again like completely positive trace-preserving unitary maps, which are denoted in the right of my slide below. Next. Okay, so that's the end of my talk. So can you just skip through to the end? So what I discussed was, oops, for that. Okay, so there are three main points I discussed. The last two are worth stressing again. So I basically pointed out some approach to study structural stability in almost dual unitary circuits or perturbed dual unitary circuits, and show that there is something like a phase transition separating structurally stable and structurally unstable dual unitaries. And I suggested a kind of slight change of paradigm of dual unitary circuits to include dual unitary interactions around the phase. And there maybe I want to point out a few challenges for future work, which I find particularly pressing. Namely, for all these results that I've been discussing, and also, which, for example, Bruno will be discussing in the next talk, it is crucial and instrumental that we have a thermodynamic limit, yeah, so that we have an infinite system, so there is no boundaries. I mean, whenever you have finite boundaries, then we have problems with this type of duality methods. So, and that's actually really pressing because we are not able to address problems like eigenstate thermalization, which are features of finite systems at infinite time, but then maybe at the end letting the size of the system going to infinity. So we really kind of need extension of these methods, if possible, to finite systems and systematic finite size corrections. Thank you for your attention.
Thank you, Tomaž, for a very exciting journey using dual unitary circuits. Yeah, here an echo. But yeah, we have time for questions.
Okay, so is it echoing?
Yeah, with some echo coming.
Okay, so okay, I just Thomas, I just have one comment. Um, the thing in the introduction of these models, since I have a control, I can I can just back wherever I want. So let me go back. Yeah, I think. Uh, Yeah, this one, this the swap into V, where is this? This is essentially one can V is a block diag. Actually, we have introduced, which is more kind of general, where the V is nothing but any block diagonal matrices, and you can be defined either swap into any block diagonal matrices or block diagonal matrices into swap. That will be dual unitary operators. And also the issue is with, if we have only with if the u is just swap into v, it is like this, its entangling power uh, will be exactly calculated. It will be less than or equals to ep store, which is some value. What I essentially want to say that it 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 unless you multiply this thing with the local unitaries, it can't be in the mixing regime. That's that's what one comment I just wanted to say.
Unless you want, can you repeat again? Unless you what?
Unless you multiply this unitary operator with a local unitary operator, it can't be in a mixing regime. It
Okay.
can't go to mixing here.
Okay, this I understand, and I think I would agree. But of course, I didn't stress that. Of course, you can always decorate this with local unitaries, right?
Yeah. So what I mean
That
to
you
say is
see
that
necessary. Okay.
its entangling power will be always less than or equals to a quantity called EP star. Suhail, can you say what is it exact
Yeah,
value?
no. The point is, I mean, the parameterization, which is there, this diagonal time swap. So V is essentially controlled unitary, so to speak. Okay, so this parameterization, if you just sort of, I mean, usually one thinks in terms of entangling power between 0 to 1. So this parameterization, for example, for qubits will span the whole, I mean, all possible dual unitaries. But for d equal to 3, for example, it will reach the maximum up to 3 by 4. So it cannot give you gates between 3 by 4 to 1, for example, in some sense, this parameterization. And what we have actually done, we have actually gone a bit beyond this construction and went up to 8 by 9, so to speak, up to, which covers sort of extended set of dual unitaries by imposing constructions on, I mean, constraints on this B alpha, that they no longer have to be blocked these uniform diagonals, but they can be block diagonals like 6 by 6 and 3 by 3 matrix, like that. So there's a one way of extending the set of dual unitaries, this set of dual unitaries, and it will have more parameters than this
Yeah,
one.
what I mean to say is that the entangling power the entangling power of the more generalized definition of this construction can go up to local, let's call q is a local dimension, so it can go up to q square minus 2 by q square minus 1. So
Yeah.
whereas this type of the parameterization can go up to
Q
I
by
think
Q.
q minus 1 by
No,
q, and
there's just a Q by Q. Q
yeah
divided by Q
it
minus
can get it can go up to q by q plus 1. So it's it is more restricted is
Okay. But
just a comment. Okay, so,
okay, yes, I understand. But if you would agree that if I add also
yes
local unit, right, this
yes
then
Yeah, but
yes
thing is, the beauty
yeah,
of this construction, which we were saying, is like if you take these B alphas to be block diagonal, not uniform diagonal, the beauty of those dual unitary set is that, I mean, one mode is guaranteed to be mixing. I mean, you cannot, no matter how you tune the locals, you are not going to get some non-variation correlations. So there is guaranteed to be some mixing happening in that particular
one
set.
of them.
One of the mode will be guaranteed to be specific, mixed, to be decaying and all.
Okay.
Okay, no, I mean, the point of my statement here was just to say that there is a simple family which is cube dimensional, right? Which goes beyond known d-square dimensional, discussed d-square dimensional families, yeah. And that I think this is kind of, asymptotically saturated, so that, if you do local unitaries at the ends, it's still a couple times of d-square, so it's still d cube, I think. I mean, we can discuss that. I don't know if you have some argument. This not the cube, but I would conjecture that D cube is kind of saturated. But okay.
Tomaž, one question about this three-partite thing, that is round of face. Matteo and Vedica also introduced one tri-unitary and then studied this correlation function. So if you are aware, what's the difference? Mainly difference between
this is very different. This is very different. I mean, what they have as tri-unitary actually can be thought of as being composed of dual unitaries. I mean, it's like it's like a three on three scatterings, which can factorize into two on two scatterings in three ways. I mean, in two different ways, but it's like three lines which cross on one point, but you can displace them a little bit, and then you can understand that they cross pairwise. Yeah. But what I propose here as as an IRF gate is something that is just it's actually trivial. I mean, it's just control on the sides, and it just has one action qubit. I mean, it's it's really. I mean, you can always actually replace IRF model with a vertex model by just changing local Hilbert space, local space dimension from Q to Q squared, right? I mean, by trading off local space dimension, you can map any vertex model to IRF model and vice versa. But then this would be a very inefficient parameterization. So you can say, I can always replace these things by brickwork gates of dimension Q squared, of local dimension Q squared. But that's very inefficient. So, no, but that's my point is it's not related to Vedica's and Hippolytis proposal.
Okay, thank you.
Thank you, Thomas. Were there any other questions?
If I may ask, hi, Thomas. Thanks for a very interesting talk. My question is about calculating correlations for observables which are on many sites. So, but they are entangled many site observables. Is there something which is there? I mean, I know that just for dual nearest neighbors, one cannot calculate that easily. In the extreme case of a Bernoulli circuit, we could show that that also vanishes. But is there some more general result for these kind of observables? And what do you expect for more extended observables?
I mean, I don't know of any explicit results other than yours, but we were thinking about this, but not more than really thinking in front of the blackboard. But the conclusion was that one can simply join wires, like one can simply group wires. Let's say you can out of four dual unitaries along the plaquette, you can make another dual unitary of size Q square, right? And now this will just show that now local operators correspond now to previous operators on two sides, right? So you can easily just do this couple of steps, kind of RG steps if you want. And then this corresponds just to, again, dual unitary circuit of larger or thicker wires, of thicker Hilbert spaces, which can have the same properties. So they are exactly propagating local operators, but now of larger support. So they give you exact correlation functions of local operators of larger support. I mean, that is a game you can start playing, but I'm not sure how, I mean, if you can do any simplifications along the way, because that comes, I mean, each time you do this step, you square the Hilbert space dimension, and you basically just show in principle you can do that. But if you can do something more.
Yeah, thanks. It's interesting proposal.
Yeah. But I think it would be interesting to start.
Yeah. Thanks. Thanks, Prosen.
Okay, so I think we did go well beyond time and into the Q&A as well. So thank you, Thomas. And yeah, it's fortunate we had the little glitch at the beginning, but I think it's good that we managed to share the slides and we managed to hear you. So thanks a lot. And I guess the next session starts in another hour and 15 minutes time. Is that right, Arvinda?
Yeah, I just check. Yeah, a minute.
Yeah.
So,
Okay,
yeah.
great. So thanks to all the speakers of the first session, and hope to see you all in another hour and 15 minutes.
Thanks, Pavaman. Thanks for chairing this session, and I thank all the speakers for this wonderful talks. And the next session begins at 6:30 p.m. IST, Indian Standard Time, and so we hope to meet you all in the next session. So, which approximately starts 1 hour 15 minutes after this.
Arvinda,
Mm.
can